Hello everyone, my name is Dr. Mihir Ghosh. I'm an assistant professor in the Department of Chemistry, SRM Institute of Science and Technology. So I hope you enjoyed my previous video regarding the coordinates in chemistry. So in the previous video we have discussed regarding the coordinate chemistry, ligands, bidental ligands, different kinds of their shapes, and different kinds of isomerism. So after that, let's discuss about the enantiomers and resin mixtures. So, what is the enantiomers? Most of the physical properties of the chiral molecule have the same boiling point, freezing point, and density. So, two enantiomers rotate the plane polarization of the light equal in opposite direction. In the last video, we have already discussed what is the plane polarized light. If one enantiomer rotates at an angle, let's say around like 32 degree to the right, the other rotates around, let's say around 32 the left, then we call it like a racing mixture. So equal mixture of two enantiomers rotate is called the racing mixture. The rotation of plane polarized light by a racing mixture is completely zero. So now we will understand this one with some having some example. Let's say we have two identical molecules. Let's say here we are showing here two molecules that rotates. So the question is like whether the CON hold to Cl2 ClX with geometrical isomers or not. So the yes, so the trans and cis isomers. So when the trans isomers and cis isomers is present, then we can see we can show the plane plate. But if the Cl is in the transform, okay. So when they are in transforms, we can see like they are completely identical molecules. So as such, you can see with the plane plate light, almost no, it cannot change the plane plate light because they are completely identical in nature. So if we do a simple operation, let's say take a molecule and use the mirror image, it is completely superimposable. So as I said, if it is like superimposable, they are not at all optically inactive. So we call it like optically inactive. But if we just change the position from Cl here to Cl here, so they will be now optically active. Because if you take the same molecule and if we change the rotation, then we can see we will not get the same molecule. Like showing here, let's say Cl and Cl are the positions. Apparently, seems like they can be like identical, but if you see, let's say, do the superimposability test, how we can do this one. Let's say if we take a mirror and make the mirror image molecule and finally try to superimpose over this one, then we can see both molecules not at all identical. So this cis isomer is basically optically active, but our transition is optically inactive. So from this molecule, we can see what kind of molecule could be enantiomers and what kind of molecules will be optically inactive and what could be the diastereomers. So diastereomers, that means there is no superimposability at all. Okay. So now let's move to the octahedral chiral complex. So the octahedral bidentate gelatin ligand, cyclin diamine, oxalate, 110 phenanthroline, etc. produces series of chiral metal complexes. Now about the bonding theories. There are three major theories of metal ligand bonding: valence bond theory, crystal field theory, and ligand theory, or molecular orbital theory. So, what is the valence bond theory? So, initially, before the CFT came, that means the crystal field theory came, initially the scientists usually used this valence bond theory to discuss about the bonding characteristics of the coordinating compounds. It is the old technique. There are some drawbacks. So this theory was used in explain to explain the geometry, magnetic property of many coordinate compounds. The basic idea of the theory is that the formation of a complex is a reaction between Lewis base and a Lewis acid with the formation of a coordination covalent bond between the ligand and the metal. This is the following assumptions. You can read it, all of this. The following assumption based on some following assumptions, valence bond theory was prepared. Okay, now we'll go to the some of the limitations. Why we particularly need the CFT. The VBT resigned raised for a period of 2 decades in the realm of coordination chemistry because of its simplicity and ease in explaining structural and magnetic properties. It could adequately explain how low spin square, planar, high spin octahedral, both low and high spin octahedral complexes. But with the progress of the time, it was having some shortcoming well noticed. So that's why we need the CFT. Mhm. So these are the major disadvantages. It fails to predict whether a coordinated complex will be the tetrahedral or square planar complex. So in the same coordination number, what kind of structure it is? It could be tetrahedral or could be square planar both. It fails to distinguish between the geometries like tetragonal, octahedral geometry, and at the same time it completely neglects excited state in a complex cannot explain absorption spectrum. Why any all the coordination complex absorbs the light. It fails to explain. It does not adequately explain the magnetic property. It is also major failure of the valence band theory. So too much attention has been given to metal ion while the importance of the ligands is not properly addressed in the valence band theory. So these are the limitation. That's why we need the CFT. But CFT have a very good nature, like it treats ligands as a point charges or dipoles. It explains the interaction between the ligands and metal d electrons mainly through electrostatic repulsions. So it can explain the magnetic nature, the characteristics color of the CF, the coordination complex. So everything now it can be explained using the CFT. Now the CFT having is was developed based on some assumption. What are these assumptions? So the first assumption, it is an isolated metal ion. All five of the d orbitals have the same energy. When ligands approach the d orbital sequence, they experience unequal repulsion and split into different energy levels. Now, shape of the d orbitals. To understand the crystal splitting, we must know the orientation of d orbitals. Some orbitals point directly along the axis, while others lie between the axis. Now, the approach to the ligands. In an octahedral complex, ligands approach along the x, y, and z axis, as we can see in this picture, like octahedral, the d orbitals have different kinds of shape. So in an octahedral complex, ligands approach along the x, y, z axis. Therefore, the d orbitals directed along this axis experience the greater repulsion. Okay, and that's why it splits into different orbitals, T2G and EG orbitals. So in the DXY, XZ, and YZ, as they are in the along the axis, they in between the axis, they face the less repulsion. That's why they become stabilized, and dx square minus y square and dz square is more repulsion from the ligands. They become unstable. So after the splitting, they having some specific name, the X, DXY, XZ, and YZ. They have the name uh, the T2G and dz square, dx square, y square thing gets the name of EG. So these are the two different levels. Now, uh, this is the very extremely important one figure. We're supposed to remember this one. The energy difference between the T2G and EG orbital is called the octahedral splitting energy, delta O. O stands for the octahedral. So we something to call it like OCT or maybe the O delta O. Delta T represents the splitting energy of the tetrahedral structure. Each T2G orbital is stabilized by zero point 0.4 delta O and destabilized by dx square z square destabilized by the zero point 0.6 delta O. Or in terms of dq also you can select stabilized by 4 dq. Dx minus y square jz dxy xz and yz and dx minus y square dz square gets destabilized by 6 TQ. Okay, and this is called the pericenter. Pericenter means where exactly before the reaction, before the ligand approach to the central metal atom, where exactly the degenerate level of energy levels was there. So this is called the BD center. So this is T2G, this is the EG. Okay. Now about this is called the crystal splitting. Okay. Now this energy gap between T2G and EG is called the crystal splitting energy, and it is denoted by the delta O and delta OCT. Mostly we write like a delta O, and where delta represents the crystal splitting energy. Because the overall energy is maintained, the energy of the 3T2G will lower by the delta, and the EG levels are raised or repelled by zero point 0.6 delta. Okay. Now about the like how we are showing here in the Titan 3 plus system. It is a D1 system, that means having only one electron. How it shows the color. So the possible reason is transition from the T2G levels, T2G1 level to EG levels. That corresponding energy gives the energy of 243 kilojoule per mole. So we are showing here in the ground state there is only one electron when, after absorbing the light of this wavelength, so it transferred to the EG levels, and due to this transition, they show some intense color. So from the CFT, now easily we can explain what kind of material showing what kind of color. So possible color we can clearly explain using this one. So tetrahedral splitting is smaller than the octahedral splitting because there are only 4 ligands and they do not approach directly. Um, uh, and do not apply to the axis, and the relation between delta T and delta is the delta T equals 4 by 9 delta. It is extremely important for mathematical calculus. Many competitive exam usually give these equations, and many numericals also usually come from this relation. Delta T equals delta 4 by 9 delta O. So this is a clear picture of the octahedral and tetrahedral structure. So here we are showing like comparative study, comparative energy diagram, like where exactly the dxy xc and yc and dxy minus dx are usually situates, and as well as in the tetrahedral where we can there from there we'll usually can see this one. Okay. So from this comparative study, we'll see the structure. Now, when to expect tetrahedral geometry and when to expect octahedral. So some of the possible reasons are that tetrahedral splitting is seldom large enough to result in pairing in the electrons. As a result, low spin tetrahedral complex are not so common. So mostly you can see that octahedral. So factors affecting the magnitude of delta. So when we will expect the higher splitting. Let's we are giving some example. So CO2 ENS3 whole 62 plus, and at the same time we can see here CO3 NH3 whole 6 3 plus. So we can see here Blatter splitting for these cases. Okay, why this is happening? So we can see here the central metal atom having in the it is in the +2 oxidation state, where the copper this is in the +3 oxidation state. So the rule says when we are getting the everything is same except the central metal having the higher oxidation state, we can expect beta splitting. Okay. Okay, what is the next one? So in the next we see like heavier analogs of the delta. So if I see like heavier analogs of the central metal atom, so we can see here the splitting actually increases to the heavier analogs. So 3D, so all having like 3D system, 3D, 4D, and 5D system. So that's why we can see here the splitting actually increase crystal flip splitting energy. Geometry of the metal unit it affects. So it is tetrahedral or it is octahedral. So we have to remember always the octahedral have the beta splitting, as we have shown in the previous slide that octahedral showing higher splitting energy. Okay. Ligands can be the RNA spectrochemicals. Yes, this is extremely important for all students. So spectrochemicals is what is that one? So all ligands have their specific capacity to split the d orbital electrons. So based on their capacity, we have a specific series. We call it like a spectrochemical series based on their ability to increase the delta, based on their ability to split the d orbitals. Who splits better, they situate in the right side, and who splits less, have a less capacity, less ability, they are in the left side. So this is the order. From there we can easily can identify if the central metal atom is same, but if there is variation in the ligand, if they are in the spectrochemical series, easily you can identify which one will give beta splitting. Okay, so this one will give the idea. So this is called the spectrochemical series. So in the next video, we'll discuss on this. Thank you.